Hello, this is Dr. Vani and welcome to my classroom. Today we'll be looking at MCQs from momentum and collision as part of the review. So the first problem, a car of mass m traveling at speed v stops in time t when maximum braking force is applied. Assuming the braking force is independent of mass, what time would be required to stop a car of mass 2m traveling with a speed v? So they are basically telling you that now the mass has changed from m to 2m, so the mass is doubled, and they are asking you to figure out the time it would take for you to stop this car of mass 2m traveling with a speed v. So it's traveling with the same speed, but now the mass is doubled. So how are we going to find the time? What concept have you all used? You all remember the impulse momentum theorem, right? F times delta t is equal to m times vf minus v naught. So keep in mind that impulse momentum theorem is simply a rearranged form of Newton's second law, because if you divide by t on both sides, this is going to be simply equal to F is equal to m times vf minus v naught divided by delta t, right? Because I'm dividing by delta t on both sides. So this simply becomes m times a, because vf minus v naught over t is acceleration. Right? Now, using the simple logic of F is equal to m times a, your Newton's second law, he said that as the mass increases, what happens to acceleration? Because keep in mind, acceleration is directly proportional to force and is inversely proportional to mass. So as the mass increases, the acceleration is going to decrease, right? So when I say the mass increases, acceleration is going to decrease, that means simply the time is going to increase by the same factor. So I'm doubling the mass here, and therefore your time is going to double, which means that it's going to become 2t. Okay, so I want to again emphasize the fact that your impulse momentum theorem, F times delta t, which is your impulse is equal to change in momentum, m times vf minus v naught, is your Newton's second law. All right, so if on the free response question, they ask you to rearrange, or if they ask you to show a relationship between Newton's second law and impulse momentum theorem, you should be able to derive it pretty easily. So let's go ahead and read the second problem. A block of mass m is initially at rest on frictionless surface. The block attached to a massless spring with spring constant k is initially at its equilibrium position. Okay, so I would always suggest that if you're not able to visualize the problem as you read the problem, go ahead and draw the diagram. Okay, so a block is attached to a massless spring. So there is a spring and an arrow is shot into the block, right? An arrow with mass m and velocity v. So it's moving, it's of mass m moving with a velocity v, is shot into the block. The arrow sticks in the block. What is the maximum compression of the spring? What kind of collision is this? First thing you need to ask yourself is, what type of collision is this? Anybody? Kirti?
Is it inelastic, perfectly inelastic?
It is a perfectly inelastic collision, right? So once you figure out that it is a perfectly inelastic collision, you pretty much understood that both the arrow and the block are going to travel with the same final velocity. And in order to figure out the compression of the spring, you use the conservation of energy, which means that the kinetic energy of the mass and the block, right? So the kinetic energy is converted into elastic potential energy, which is 1/2 kx squared. And I know that the kinetic energy is 1/2 mv squared equals 1/2 kx squared. Now, I can get rid of 1/2. I know the mass because the mass is simply going to be the combination of the two masses, the mass of the arrow and the mass of the block. However, I do not know the velocity, right? Because I do not know what is the velocity of the block and the arrow once the arrow goes and gets embedded in the block. So I need to figure out that velocity. And to figure that out, you know that you can use the concept of conservation of momentum, right? So the mass of the arrow times the velocity with which the arrow is traveling plus the mass of the block, and initially the block is at rest. So V is equal to 0 in this case. So therefore, the initial momentum of the block is going to be equal to 0. Would be equal to m plus m, because the two masses are getting embedded together upon collision, and they move with a velocity of, let's call that Vf. So I figured out that Vf would be equal to mv divided by m plus m. Now I can use this final velocity in here for the kinetic energy and figure out what my x is going to be equal to. So in place of m, I'm going to plug in m plus m because it's the combined mass of the two objects times the velocity squared, and that's going to be mv over m plus m whole squared. And that's equal to kx squared. So now you notice that here I can write this as mv whole squared divided by m plus m whole squared, and I have m plus m here. And this can be reduced. I can reduce this. I can get rid of that square there, right? And now you're left with mv squared divided by m plus m is equal to kx squared. So I can divide by k. So I can bring k to this side, and the k is going to go in the denominator here. And so I can get rid of k, and then you square root on both sides. And when you square root, the square and the square root for mv is going to go away, leaving us with x is equal to mv divided by square root of k times m plus m. And therefore your answer is going to be D. This, I actually noticed that it was a free response question. Here they gave it to you as a multiple choice, but in the past I have seen this as part of free response question. So it's a very, very important problem because this concept comes to you in different forms, and for sure we see it on pretty much every year's AP exam. It appears in some form or fashion. Okay, this concept will appear for sure. P and Q have the same momentum. Q can have more kinetic energy than P if it has A, more mass than P, B, the same mass as P, C, more speed than P, and D, the same speed at P. What would be your answer and why? Keep in mind that momentum is the product of mass and velocity, right? So when you say two objects have the same momentum, then obviously if one of the objects has more velocity, then it should have less mass, okay? If the object has more mass, then the velocity is going to be less in order to maintain the product the same, right? So here they're telling you that Q has more kinetic energy than P. When it has more kinetic energy, it's very obvious that kinetic energy is 1/2 mv squared. When they say it has more kinetic energy and the two objects have the same mass, same momentum, then obviously it is understood that the velocity of Q must be more than P, or the speed of Q must be more than P. So the answer to 3 is C. It's a very easy conceptual question. If you can understand that if the mass of the velocity of the object increases, then the velocity decreases in order to keep the momentum the same, because they are specifically telling you here that the two objects have the same momentum, and therefore if the kinetic energy of Q is more, then obviously its speed is going to be more than P, and its mass is going to be less than P in order to maintain the same momentum. Okay. 4. A spring is compressed between two objects with unequal masses M and capital M and held together. The objects are initially at rest on a horizontal surface. When released, which of the following is true? The total kinetic energy is 0. The two objects have equal kinetic energy. The speed of one object is equal to the speed of the other. The total final momentum of the two objects is 0. The two masses are compressed, are compressing a spring and are initially at rest, which means that the initial momentum, right? The initial momentum is equal to 0. If the initial momentum is equal to 0, according to the law of conservation of momentum, the final momentum of the system also should be equal to 0. The total momentum of the two objects before collision and after collision must be the same. So if the initial momentum is equal to 0, and you all agree that it is equal to 0 because the two objects are at rest, right? Then the final momentum must also be equal to 0. So the answer to 4 is D. The total final momentum of the two objects is 0. Okay, let's look at 5. Two football players with mass 75 kilograms and 100 kilograms run directly towards each other with speeds of 6 meters per second and 8 meters per second respectively. If they grab each other as they collide, the combined speed of the two players just after the collision would be, what would it be? In conservation of momentum, what would your equation look like? It says 75 times 6 meters per second, right? Plus 100 times negative 8 meters per second would be equal to 75 plus 100 times V. Do you all agree with me? And so if you solve it, 75 times 6 minus 800 divided by 175, what would you get? Because they're asking for speed, we don't have to worry about the direction. You get it as V as negative 2 meters per second. However, the negative sign simply indicates that the object is moving to the left. The two players are moving to the left when I say object, with a speed of 2 meters per second. Okay. Now, the common mistake that students do, I'm warning again and again, is they forget the sign. They forget this negative sign here, negative 8 meters per second. They told you that the players are coming in opposite directions. So obviously, if you consider 6 to be positive, then 8 is going to be negative. And if you forget to put this negative sign, you're going to obviously end up having a different answer. Okay,